Thank you for the introduction. And this work is a collaboration with my previous PhD supervisor, Richard Wu, at Tsinghua University in Peking, China. And so this work, I try to understand like a very simple question, like if you have data and somehow of each users, how can you get the relationships between different users and how this relationship change with time. So I will start with the data and the final results we get, just to give you a direct impression that what we can do. So we look at the word indices by WRDS. This is from this website, from Wharton. And we look at the weekly average of absolute logarithm of the daily word indices from 2006 to 2022. There are in total more than 810 points. And so because we take the absolute value of the logarithm, it's a measure of volatility and risk. So the network between these indices is also like a measure of the systematic risk. So if every country is highly correlated to each other, then there's a risk it will transfer very quickly in the network. So what we finally want to develop is like a tool where you can somehow so what we do is first we estimate the correlation function between each pair of countries, and we build a simultaneous confidence band. By simultaneous confidence band, we mean that like we can control the error rates alpha, so that with the probability y minus alpha, this correlation function always lies in this band. And after deriving this confidence band, we can infer the time varying network, but just checking if the zero lies in the confidence band. So if zero is not lying in the confidence band, it means like the correlation is significantly not zero. So the advantage of this method is like we can have a smooth view of how the correlation changes with time, and we can clearly see like when the changes happens, and we can correspond it to like different events that's happening. So for example, at the beginning, this is like we took like 6 countries in total, and this is just like I took out like 3 countries just for visualization and demonstration. So at the beginning, like cannot see like at the beginning, so all these 3 countries, Japan, France, and China, are connected, and because like you can see like the zero is not contained in the band at this time point. However, as we moved a bit forward at 2012, we can see that there's like a zero like lies in these 2 bands, all these 3 confidence bands. So it's suddenly like every country is not connected, and it can be connected to the event that happens in the January 13th of 2012, was in the middle of European sovereign debt crisis. And then as we move forward to 2014, we can see like the changes occurs again, and like there are some correlation that is significantly not zero. So we see that there's like connection between Japan and France within China. And we can see that there's like on May 25th of 2014, during the high-level economic and financial dialogue between China and France. And there's like also conflict between China and Japan in the East China Sea. And finally, at the end of 2018, we can see like the dynamic change again. And on the July 6th of 2018, like there's like the trade war between China and United States begin, and so we just don't see like this. So in this network, there's no connection between China and France. So back to the mathematical formulation of the problem, like a bit more strictly, we start with the most simple case where we have a panel. It's a vector time series, a time series vector, where no, it's not a time series yet. Also, it's just like ID vectors. We have y, yi to yp, and at each time we have independent observations. So the question is like, what is the relationship within this between each pair of nodes? So we want to infer from these random vector sequences to a network. And this is like a very classical problem already. There are many research in this area. Basically, like you can calculate the correlation between each pair of nodes, but the question is, how can you decide the threshold that when this correlation is large enough, and then you connected the edge between these two nodes? And there's like literature from Efron on the large scale inference, and these two authors on the association graph on this topic. However, as we have like time series, like multivariate time series, we have more challenges because first, like we don't have this independence anymore. And in the literature, it's like mentioned that this dependence actually would bring like a problem in the inference from the ID assumption, because like the previous procedure would not really work. And the second problem we want to address is since we have time series, like we can get something more than just one time work, one network. What we can get is a time varying network. Like at each time point, like there's a network, and it evolves with respect to time. And these evolving features of connectivity is also like attracting a lot of attention from different domains, like in finance or biology, and they want to know what is the dynamics between different entities. So at the end, we formalize this problem as a multiple testing problem. So on the first line, what we have is not just one hypothesis, but just it's like a series of hypotheses between different nodes. So we have this H0 ij. So the Cij t is like understand it like the correlation function. So we want to know like if it's zero or not zero. And further, we can extend it a little bit more to include more indices like measures for each pair of nodes, so that we will connect two nodes, like for example 1, 2, if there is 1k and this measure, for example, not equal to 0. But actually, we can also generalize it, like we can test whether it's equals to another function. And so in this paper, we primarily focus on the case where this C is the correlation function, the K is the lag K in the correlation function. And we can also extend it a little bit more to have measures beyond linearity. Okay, so and as I've mentioned before, like what we want to do is to estimate the correlation function and build a confidence band, and so that we can just infer at any time point, and the probability that we make a mistake is is uniformly controlled, not only across the time, also among different pairs of nodes. So for example, here, like you can just look at it, t equals 0.3, and you have this correlation function, and you have the confidence band, and you can just see like if this 0 is contained in the confidence band. So for this between 1 and 2, like you can see like here, like the 0 is not in the confidence band, so we can connect these two nodes. So mathematically, we just formulate this as like a simultaneous inference problem, and we control this T and all pairs of nodes and all the legs uniformly, so that the uncertainty in this inference is uniformly controlled. So I just want to give you an overview of how this whole procedure works. And this is also the reviewer want to see like a flowchart of everything. And so what we have, the time series vectors we have is like a net stationary. We don't need like stationary assumptions, but somehow the changing mechanism is smooth with respect to time. And there's one part. The other part is like it can have some unknown structure breaks. So you can see that it's not very clear here, but like you can see like by some chain point detection algorithm, we can see like these time series have like multiple chain point at different locations. And what we want to do is to have like estimation method that is robust to the potential chain points, which like the number can also grow with respect to the sample size. And so we want to estimate the correlation function. We want to estimate the variance of the correlation function. And at the end, we want to derive an approach to decide this time variance threshold, where when your correlation is large enough, is beyond this threshold, then you can connect an edge. So from left to right, it's just at the beginning, we have a series of time series vectors. And then we have like the correlation, and we have the time variance threshold, and at the end we'll derive like a series of like time varying networks, and we will control the uncertainty at the level of alpha. And as I've mentioned, like the time series we consider is consists of two parts. The first part is like there's like potential structure changes, and the second part is like locally stationary. It means like if you look at the one point, the neighborhood is stationary, but it's kind of, if you look at the whole time series, it's non-stationary, but locally you can approximate it by the stationary time series. And by the way, like the number of the change points can also be growing with respect to the sample size. It can also of course, it can also be fixed. Yeah. So so we want to have a robust estimation of the correlation function. The approach we do is just to take a difference of the original time series, so that we just want to somehow automatically eliminate the effect of chain points. And we can see that under some short-range dependence, if you look at the product of these two differences, it's somehow is like the expectation is the linear combination of two correlation functions. Yeah, and here, if you take the same leg that is large enough, then you will get the variance function. That's the motivation, like how to derive the correlation estimates from the original time series. So afterwards, we just do the local linear estimation based on the differences of the original time series. And then we transform it back, because what we estimate is the linear combination. We transform it back and then we get the original correlation the covariance function, and we can calculate the correlation function. And the next thing we consider is to do a variance reduction. So why is it very important? Because our target is the correlation function, and it has a natural support between -1 and 1. So if our estimate of confidence band exists, -1 and 1 is completely not useful. So if it's too wide, it's not useful. So if we can reduce the width of the confidence band, then like it's more informative. Like there's a chance that we can compress it like between -1 and 1. Then we can get more information. So as you can see, like in the real data, what we really do is like in the solid line, there was the difference space estimation, and the dashed line is like we use variance reduction. So you can see that the original confidence band is too wide, like it can go beyond 1. And after the variance reduction is narrower and is more informative, we can use the whole band. Yeah. And the idea of this variance reduction approach is so we have the original kernel estimate of beta, and then we calculate the right neighborhood by combining these 3 points. And we also calculate the left neighborhood by combining 3 like design points, and then we combine them together. So the idea is just to combine these 2 estimators to cancel extra bias. Yeah, and then finally we will show that this whole approach and this time varying threshold here will actually lead to a valid inference procedure. So what we finally get is like we can uniformly control the type 1 error. So this T here is the normalized correlation, and R is the bootstrap pointile. You can it also appears here, so it just divided here. And then the second one is we can control the probability of recovering the true time varying network structure. That means like it can include the type 1 error and also includes the type 2 error. We can guarantee it's not less than 1 minus alpha. And the second result is like for the variance reduction, we can show that compared to the original one, like we have a uniform variance reduction in the sense that the width is uniformly smaller than 1 and across one time, because the width here is this bootstrap pointile times the variance. And this is before the variance reduction, this is after the variance reduction. So the key challenge here is how to control like these 2 bootstrap pointiles before and after the variance reduction. Yeah, so at the end, we can show that we can improve the probability of recovering the time varying network conditioning on data. And so this is just one procedure in the proof. It's because we want to analyze the bootstrap quantile behavior, which is like it's a Gaussian distribution. So we use the results from Roy 2014 as like a Gaussian correlation conjecture or inequality. It says like this PAB, like if a person has both normal and weight and height, can be lower bounded by the independent case, like this the probability of the person has normal weight times the person has normal height. So this is solved by a retired German statistician in 2014 when he's brushing his teeth. And yeah, it's like, so a lot of people have been working on this for many years. And finally, we can show some simulations where we consider like locally stationary time series. This is like a time varying AR process where the coefficient change with time. And we consider different settings. We have a lot of like 1 change points or 3 change points or more change points. At the end, we just want to show that so for different sample size, if we use this variance, it's called red here, is the variance reduce approach, we can always achieve a width reduction with the control simulated recovery rates of the whole network. And we can also have a time varying visualization of the proposed procedure that it can always reduce the simulated false negative rate. That's all. Thank you.